Hello students, welcome to the online lecture series of Basics of Computer Network. Myself, Assistant Professor Mr. V.R. Vadekar from Department of Electronics and Telecommunication from Maturji College of Engineering and Research Center, Nasik. Today we are going to discuss about types of signals and multiplexing techniques and digital signals. But before that, have a quick revision that what we have studied in last lecture. Guys, in last lecture we have seen about introduction to data communication. That what are the characteristics of data communication? What are the different blocks involved in data communication? Then we have seen different topologies as like your mesh topology, star topology, ring topology, bus topology, and hybrid topology. And we have seen the advantages and disadvantages of them. After that, we have seen about the networks, that is your types of networks, LAN, MAN, and WAN. So today's topics that we are going to discuss is your types of signals. Starting with types of signals. As we know guys, that data, it could be in the form of your analog or it could be in the form of your digital form. And in order to transmit the data, it must be transformed into electromagnetic signals. Whatever I am speaking, it is in analog data. It is an analog data. Human voice, it is analog data. So whenever I am going to speak, it is going to create an analog wave in the air. And this is captured by your microphone. And then microphone, it is going to convert into your analog signal. And then later on, if we want to transmit it, then we are going to sample it, quantize it, and make it into digital form. So it is all about your analog data. And digital data in the sense what? The data which is stored in your computer in the form of zeros and one. Similarly, there are signals, analog signals or digital signals also. And as we know, since it is analog, it means what? It is continuous and it is taking a continuous values. And digital data, they have a discrete state, take on discrete values at a particular instant. And similarly, the signals can also be analog or it can also be digital. Analog signals which can have infinite number of values in a range, and digital signals, it can have only what? Limited number of values. So you can see on this screen that this is your analog signal which is continuously going to vary with respect to time, and this is your digital signal which has a value at a particular instant, at this instant, at this instant, at this instant, and rest it is a zero. So it is in the form of your what? 1 and 0. Now in data communication guys, we commonly use periodic analog signals and non-periodic digital signals. So please keep it in your mind. Now this is the analog signal. You can see it is continuously varying with respect to time. And this is your digital signal, which is going to represent your positive logic, that is 1 and 0, which is represented by negative voltage. Now, what is periodic analog signals? Periodic in the sense, a signal which is going to repeat itself, its pattern, it is going to repeat itself after a specific duration, after a specific time. Whereas non-periodic, it is a random kind of nature. We couldn't predict it. We couldn't find its period, time period, because it's random in nature. So basically periodic signals, it can be classified as a simple signal or composite signal. A simple periodic analog signal, it's just a sine wave and it can't be decomposed into a simpler signals. A simple sine wave is just a simple periodic analog signal. And whereas a composite periodic analog signal, it composed of multiple sine waves. When the multiple sine waves we are going to use and compose to make a one signal, it is nothing but your composite signal, mixture of different signals. So basically, sine wave, which is the basic building block of any signal, it is described by its amplitude, period, or frequency and phase. You can see this is the waveform of a sinusoidal wave. This is a sine wave. This is the amplitude. Y-axis, it is going to determine its amplitude. Whereas x-axis, it is going to be what? It is your time axis. So it is going to change with respect to what? Time. Now, first we would discuss about the amplitude. You can see on the figure. Amplitude, it is nothing but it is a highest or absolute value of its highest intensity, which is proportional to the energy it carries. And remember, for electrical signal, the amplitude, it is measured in volt. So this is a signal which has a high peak amplitude. And this is a signal which has what? Low peak amplitude. So amplitude, it is going to vary depending on the signal. So it is what? It is an absolute value of its highest intensity. It is amplitude. Now, period. Basically, period and frequency, these are the, are inverse of each other. You can see on the, screen, basically period, it means what? Period, it means amount of time in seconds, amount of time in seconds a signal needs to complete one cycle. See, you can see on the figure, amount of time which is in second a signal needs to complete one cycle. This is your one cycle. So it is called a period. This is called what? Period. This is a period because amount of time taken by this signal to complete its one cycle. And then what is frequency? Frequency refers to the number of periods in 1 second. See, this is 1 second. This is the duration of what? 1 second. So, number of cycles, you can measure it, you can count it. There are 12 periods are there, 12 cycles are there. So, which is going to complete in one cycle? So, frequency refers to what? Number of periods or number of cycles in 1 second. So over here in 1 second, how many periods are there? 12 periods are there. So what is the frequency? Frequency is 12 hertz. And remember, period and frequency, they are inverse of each other. So if frequency is 12 hertz, what is the time period? It is 1 upon 12. That is second. And period, it is measured in time, that is in second. And frequency, it is measured in hertz. This is first example. Second example, it is, you can see that how many cycles are there, you can measure it. This is a one complete cycle, second complete cycle, third, fourth, fifth and sixth cycles. So how many cycles in 1 second? In 1 second, 6 cycles. So what is the frequency? It is a 6 hertz. So what is a period? It is inverse of frequency, that is a 1 upon 6 second. Getting, guys? And frequency is denoted by small f and period, it is denoted by capital T. So f is equal to 1 upon T, or we can say capital T equal to 1 upon f. Now this is the table of, the period and the frequency. See, second is equal to 1 second. Millisecond, it means what? 10 raised to minus 3 second. Microsecond denoted by this one, 10 raised to minus 6. Nano, it means 10 raised to minus 9 second. And pico in the sense 10 raised to minus 12 second. It is units which is of periods. And these are the units of your frequency. Hertz denoted by Hz. Kilohertz means 10 raised to 3 hertz. Mega means 10 raised to 6. Giga means 10 raised to 9. And tera means 10 raised to 12 hertz. So you please note it down these, because in numerical or in further lectures you require this one. So frequency, it is a measurement of the rate of changes, and changes in a short span of time means high frequency. Exactly. And changes over a long span of time means low frequency. If period it is high, then frequency is low. And if period is low, frequency is high, because they are inversely proportional to each other. And two extremes, that is, there is a no change at all, it means a zero frequency. And if instantaneous changing the frequency it is going to change, then we can say it has a infinite frequency. Now, third characteristic is a phase. So phase, it is going to describe the position of this waveform relative to time zero. You can see it over here. This is your zero, time instant equal to 0, origin. So if it is going to originate from 0, it means it has a phase of 0 degree. See, this is 0, this is 90 degree, that is pi by 2. This is 180 degree, that is pi. This is 270 degree, and this is your 360 degree, that is 2 pi. And remember, phase is always measured in degree or a radian. Degree in the sense 0 degree, 90 degree, 180 degree, 360 degree, like that one. And in the form of a pi, that 0, pi by 2, pi, 3 pi by 2, as like, or 2 pi, it is nothing but your radian. And what is radian? 1 radian is equal to 360 upon 2 pi. You can write it. What is 1 radian? Is equal to 360 upon 2 pi. Getting, guys? And see this second figure. You can see that this signal, it is being delayed by 1 by 4 t seconds. T, it is a time period. So you can observe it, it is going to origin, it is going to occur at 90 degree. This is your 90 degree. So phase of this signal, it is what? 90 degree. And similarly, if it is going to occur at this instant, so it is delayed by 1 by 2 t second. So it means what? It has a degree, how much it is? 180 degree. That is pi by 2. Okay. Now, moving towards the mathematical, how we are going to represent a sine wave in mathematical form. Always remember, guys, we always represent sine wave in the form of your A into sine omega t plus phi. What is phi? It is your phase. Omega in the sense what? Angular frequency, and omega is equal to 2 pi f. Okay. And A, it is nothing but your amplitude. So you can see this, take this example. This is a sine wave whose amplitude, it is a 5 volt, and this is your time axis, x-axis, which is of time duration. So you can see it is of 1 second. In 1 second, how many cycles are there? You can count it. 1, this 2, this 3, and this 4. So what is a frequency? It is a 4 hertz. It is being written over here. And since it is going to origin, it is going to occur at origin. So phase equal to 0. And what is amplitude? Peak voltage. Peak voltage, it is what? 5 volt. So how you are going to represent this equation? S of t is equal to A. A means 5 sine of omega t. What is omega? 2 pi f. So 2 pi f. What is f? It is a 4. T plus phi. That is a phase. But phase over here equal to what? 0. So the required equation, it is what? Equal to find sine of, in bracket, 2 pi 4 t plus 0. Now you can see the second example. Second example, you can see over here the amplitude, it is a 10 volt, and you can count the number of cycles in this 1 second, it is 8. And since it is going to occur at origin at this instant. So phase equal to 0. So how you can represent it? A it is what? Amplitude, peak amplitude, sine of omega t. What is omega? That is angular frequency, which is equal to what? 2 pi f, linear frequency. F equal to what? 8 plus phi equal to 0. So this is the required mathematical equation for your second wave. Similarly, you can see the third wave. Third wave, you can see it over here. There is a phase. What is a phase? It is your pi by 2. Okay. It is pi by 2. Pi in the sense, it is what? Your 180 degree. Earlier, sorry, I told about over here it is a pi by 2. It's not pi by 2. Basically, it is a pi. By mistake, I told it. So just correct it. It is a pi. Pi means 180 degree. Okay. So now A equal to 5 and F equal to 2. How many cycles are there in 1 second? You can measure it. It is a 2 cycles are there. So frequency is 2 hertz and phi is equal to pi by 2. That is 180 by 2. That is the 90 degree. So how you can write it? S of t is equal to A, that is 5, sine of omega t. Omega in the sense 2 pi f. F is what? 2. So 2 pi 2 t plus phi. Phi kitna hai? Pi by 2. So you can write it pi by 2 over here. So this is the desired mathematical equation for your sine wave. Now moving towards the next, that is your wavelength. Now another characteristic of a signal traveling through transmission medium, it is nothing but your wavelength. Wavelength, it is going to bind the period or the frequency of a simple sine wave to the propagation speed. Wavelength is denoted by lambda, and whose formula is equal to what? It is equal to the propagation speed, that is denoted by c into period. Right? Or period is equal to, you can denote it by as 1 upon f. So we can write it propagation speed is equal to 1 upon f. And you can see the signal which is traveling, a light wave, it is traveling with a speed of light, that is 3 into 10 raised to 8 meter per second. So that's why we have denoted by it is a c. You can see from the figure, that is the wavelength, how you are going to represent that. This is a transmission medium at time t, and it is delayed by plus capital T, t plus t. And this is nothing but your wavelength, which is equal to what? Propagation speed into period, time period. That at what speed does wave it is going to travel, and this is the direction of your propagation. Now guys, we are going to see now the time and the frequency domain. So a complete sine wave in the time domain can be represented by a one spike, single spike in the frequency domain. You can see on the figure that this is your sinusoidal wave, which has a 6 cycle in 1 second. So whose frequency is 6 hertz and amplitude is a 5 volt. So if you want to represent this sine wave, whose y-axis is denoted its amplitude and x-axis is going to denote the time, that is a time domain plot. If you want to represent it in a frequency domain plot, so you can represent this whole wave as a single spike which is at 6. Why 6? Because frequency is 6 hertz. This x-axis, it is going to denote the frequency, and this is going to denote your what? Amplitude. Understood guys? So time domain, it is going to compare your instantaneous amplitude with respect to time. See it over here. Instantaneous amplitude, value of this amplitude with respect to time. And the frequency domain, it is going to give you the peak amplitude with respect to frequency. टाइम डोमेन में हमको क्या पता चलता है, इंस्टेंटेनियस वैल्यू ऑफ एम्पलीट्यूड पता चलता है, मगर यहां पे इन फ्रीक्वेंसी डोमेन वी गेट द आइडिया ऑफ इट्स पीक एम्पलीट्यूड ओनली. गेटिंग? Now we have taken the example of three sine waves with a frequency 0, 8 and 16. So you can see that a blue color, blue line, it is a straight line. Since period, it is undefined, infinite. So what is a frequency? 1 upon time period, that is 1 upon infinity, which is 0. So frequency, it is a 0. That is a time domain plot. So if you want to represent the frequency domain, then you are going to represent its amplitude, that is a 15 volt, but at a frequency what? 0. So we have denoted here like this one. Similarly, the sinusoidal wave which is shown in the pink color, it has a total cycle of 8 cycles in 1 second. So frequency is what? 8 hertz. But amplitude, it is decreased, that is of 10 volt. So you can see the frequency domain plot, that it is going to tell you the peak amplitude 10 volt at a frequency 8. And similarly, the green waveform, it is in the form of what? Has amplitude 5 volt, but it has a 16 cycles in 1 second. So what is the frequency? 16 hertz. So if you are going to represent it in frequency domain plot, you can see this is your 5 volt green color, but frequency 16. So hope so you understood this time domain and frequency domain of sine waves. Now what is composite signal? A single frequency sine wave is not useful in data communication, guys. We need to send a composite signal, a signal which is made up of many sine waves. And when we are going to change one or more characteristic of a single frequency signal, it becomes a composite signal made up of many frequency. And guys, in the early 1900s, the French mathematician, J.B. Fourier, they showed that any composite signal is a sum of set of sine waves of different frequencies, phase and amplitude. So according to Fourier analysis, any composite signal can be represented as a combination of a simple sine waves with different frequencies, phases and amplitude. And if the composite signal is periodic, then the decomposition gives a series of signals with the discrete frequencies. And if the composite signal, it is a non-periodic, then the decomposition gives a combination of a sine waves with a continuous frequency. So it is one of the most important thing that is being told. So please consider this. Now you can see a composite signal. Now we have added these 3 harmonics. If you can see on the figure, 3 harmonics are there. F, frequency 3F shown in blue color, and frequency 9F shown in black color. So these 3 harmonics, we are going to add it, and we are getting a waveform closer to the square wave. It is not exactly a square wave, but we get something which is close to, not exact, which is close to square wave. So if you want a square wave, perfect square wave, then definitely you have to add more and more harmonics. Here we have add only 3 harmonics, but you have to add more and more harmonics in order to get a pure square wave. Understood, guys? So this is the waveform which is the addition of these three harmonics. And if you want to represent these composite signal, which is in time domain, you want to represent in frequency domain, you can plot it. You can see it over here. That frequency F, 3F and 9F, we have denoted it. And see how the amplitude it is going to reduce. The peak to peak amplitude it is going to reduce. So this is a frequency domain plot of your composite signal. Now see, it is your non-periodic, composite non-periodic signal. See, this is your non-periodic. You don't know that what is a period. It is a random in nature. It is non-periodic. And it is a frequency domain plot of this non-periodic signal. As I already told, that composite signal is a non-periodic, then the decomposition gives a combination of sine waves with a continuous frequency. So it is a type, a type of a sine wave. Non-periodic it is there. Na? So it is a frequency domain of this sine wave. And different frequencies are there. See, the frequency it is going to vary. Instantaneously it is going to vary. So it is a composite non-periodic signal. Now talking about the bandwidth. The range of frequency that a medium can pass is called a bandwidth. What is? The range of frequency that a medium can pass is called as bandwidth. And because no medium can pass or block all frequencies, so the bandwidth normally refers to the range of frequency that a medium can pass without losing 1/2 of the power contained in that signal. And remember, the bandwidth of a composite signal, it is the difference between the highest and the lowest frequency contained in that signal. So you can see from the figure, if you want to calculate the bandwidth, you can see that if a medium it is going to pass a frequency between 1000 and 5000 without losing most of the power contained in this range, the bandwidth is what? 5000 minus 1000, that is 4000 hertz or 4 kilohertz. And remember, the bandwidth, it is a property of a medium. So similarly, this is a bandwidth of periodic signal. This is a bandwidth of a non-periodic signal. Formula remains same, that is a highest frequency minus your lowest frequency contained in that signal. It is your give you bandwidth. Now, let's take one example. A signal has a bandwidth of 20 hertz and the highest frequency is 60 hertz. So what is the lowest frequency? And draw the spectrum if the signal contains all integral frequency of the same amplitude. As we know, that bandwidth is equal to FH minus FL, that is the highest frequency component minus low frequency component. Bandwidth is 20 hertz, FH is equal to 60, which is given. You have to calculate FL, that is the lowest frequency. So lowest frequency is equal to 60 minus 20, that is 40 hertz. And this is the spectrum. Since it is going to lowest frequency, it is going to start from 40 and highest it is of 60. And bandwidth is equal to what? It is 20 hertz, that is 60 minus 20. 60 minus 40, that is 20 hertz. So you can plot the spectrum, that is 40, 41, 42 up to 60 hertz. So you can see carefully this diagram, that how we have plotted the spectrum. If you got the lower frequency component, higher frequency component, then bandwidth is equal to highest minus lowest, that is 60 minus 40, 20 hertz. Now guys, moving towards the digital signals. So you can see on the figure, when the data it is represented by means of a binary, that is a logic 1 and logic 0. So over here you can see that binary 1 it is represented by a positive voltage, whereas binary 0 is represented by 0 voltage. So again, it is a digital signal with two levels are there. Why two levels? Because 1 and 0, only there are two levels are there. Level 1 it is 0 and level 2 it is a 1. That is, it has some positive voltage. So you can see it on the screen that this is a duration of 1 second. And how many bits are there if you count it? 1, 2, 3, 4, 5, 6, 7, 8. That is 8 bits sent in 1 second. So what is a bit rate? Bit rate in the sense what? Number of bits transmitted in 1 second. So over here, 8 bits are transmitted per second. So what is a bit rate? It is a 8 bps, that is 8 bits per second. It is for what? A digital signal with two levels. But similarly, if you have a digital signal with four levels, you can see it level 1, level 2, level 3 and level 4. Since this signal element, it has a 2 bits, that is 0 0 0 1 1 0 and 1 1. 4 possible combinations are there, guys. Please understand it. Over here 2 levels are there, 0 and 1. Over here 4 levels are there. What are those 4 levels? 0 0 0 1 1 0 and 1 1. These are the 4 possible combinations if you have a 2 bits. Since each signal element, it has what? How many bits? 2 bits. This is called a signal element. So possible combinations, there are 4 possible combinations. So 1 1, it means it has a highest positive voltage. 1 0, it has a low positive voltage. 0 1, negative voltage, and 0 0, it is the most negative voltage. So you can see 0 0, it is represented by level 1, and 1 0, it is going to represented by level 3. 0 1, it is going to represent by level 2, and 1 1, it is going to represented by level 4. So these number of bits per signal element, it could increase. Over here it is a 2, so you can take it 3 also. So there would be 8 possible combinations, as like your 0 0 0 0 1 0 1 0 0 1 1 1 0 0, as like that one. So from this figure you can see that this is your bit rate. What is your bit rate? That is 8 bits per second. In 1 second we are going to transmit 8 bits. So 8 bps, it is your bit rate. What is interval? In 1 second, 8 bit intervals are there, right? So the duration of a 1 bit, it is nothing but your bit interval. This is total duration, it is of 1 second. For 1 second, it has how many intervals are there? 8 intervals are there. So what is bit interval? It is a duration of each bit, duration of 1 bit. That is your bit interval. And the number of bits transmitted per second, it is your bit rate. Now assume, guys, we need to take one numerical. Assume that we need to download a text document at a rate of 100 pages per second. We need to download some PDF which has 100 pages per second. So what would be the bit rate of the channel? And if each PDF, each page of that PDF, it is an average of 24 lines, and each line, it has 80 characters in each line, and we assume that each one character requires 8 bits, then what would be the bit rate, guys? Could you think? It is simple. It is 100 pages into 24 lines into 80 characters into 8 bits is equal to 1.536 Mbps. That is a megabits per second. Right? This is in bits per second. So you need to convert into this megabits. So hope so you understood this numerical. It is a simple one. Now digital signal as a composite analog signal. As I already told in Fourier analysis, the frequency domain representation of a periodic signal, it is a discrete frequencies. See, it is a digital signal which consists of many sine waves. So if we do the Fourier analysis, then it consists of what? A different frequencies, which is shown over here, f, 3f, like this one, right? And since it is a non-periodic, and as I already told, the non-periodic signal, it is represented by a continuous sine wave. So this is a time domain representation of your non-periodic signal, and it is your frequency domain of your periodic non-periodic signal. And this is a frequency domain of your periodic signal. And remember, digital signal, it is as a composite analog signal. It consists of many sine waves. So the Fourier analysis of your periodic digital signal, it gives you the discrete frequencies. This discrete frequencies is going to tell you it consists of these many of sine waves whose frequency has f, 3f, 5f, 11f, 13f, and so on. Now the transmission of digital signal, guys. A digital signal, it is a composite analog signal with an infinite bandwidth. And a baseband transmission. What is baseband transmission? When you are going to sending a digital signal without changing into analog signal, you are going to sending it as it is. Then we call it as a baseband transmission, right? So baseband transmission of a digital signal that is going to preserve the shape of a digital signal is possible only if we have a low pass channel with an infinite or a wide bandwidth. Low pass channel. How to recognize low pass channel? When the frequency of that channel start from 0 to a particular frequency range. See, it is a f1. It is a narrow bandwidth, but it has a wide bandwidth. Or ideally it should be infinite, but practically it is not possible. So it is moving towards a infinite frequency or very large bandwidth. So it is a low pass channel. Low pass channel, it means whose frequency is going to start from 0. Now you can see the next, that is low pass channel with a wide bandwidth. So over here you can see that the input signal, it has a bandwidth that is 0 to infinity, and it is a non-periodic digital signal. You have to pass it through wide bandwidth channel whose frequency ranges from f1 to f2. And remember guys, f1 it is closer to 0 and f2 it is closer to infinity. Understood? Because no one bandwidth channel, it has a frequency ranges from 0 to infinity. And since it has a frequency f1 to f2, so you are going to see the output whose shape is more closer to this input signal, that is a digital signal, and whose frequency ranges from f1 to f2, because it has a range of frequency of this channel. Ideally it should be 0 to f, but f1 which is closer to 0 and f2 it is closer to your some frequency towards your infinity. Now bandwidth requirement. You can see in baseband transmission, the required bandwidth is proportional to the bit rate. That is, if you need to send the bits faster, you require a more bandwidth. You can see it over here. If n equal to 1 kbps, bandwidth required is a 500 Hz for harmonic 1 only. And if you need to send the more bits faster, that is a 10 kbps at a rate of 10 kilobits per second, you require a bandwidth of 5 kilohertz. And again, you need to improve the speed, that is 100 kilobits per second, then definitely the bandwidth it is going to increase, that is a 50 kilohertz. This is for harmonic 1. But if there is a digital signal which consists of a 2 harmonics, suppose harmonic 1 and 3, this is a bandwidth requirement, that is n for 1 kbps, bandwidth is 1.5 kilohertz. But if you need to increase the bit rate, that is a 10 kbps, then the bandwidth is going to increase 15. Again, you are going to increase the bit rate, that is 100 kbps. Again, bandwidth is going to increase 150 kilohertz. And similarly, it is for harmonics 1, 3 and 5. So The conclusion is that the required bandwidth is proportional to the bit rate. If you need to send the bits faster, you require more bandwidth. Broadband transmission, or which is also called as band pass transmission, which has a bandwidth between f1 and f2. Band pass, it has a particular band. If available channel, it is a band pass channel, we can't send the digital data signal directly to the channel. Remember, we need to convert that digital signal into analog signal before transmission. For digital signal, in order to transmit the digital signal, we always required a low pass channel with wider bandwidth. But if you don't have a low pass channel, you have a band pass channel, that is a frequency limited to f1 to f2, then you need to convert the digital signal into analog signal before transmission. This is the most important thing. In low pass channel, the lower limit is towards zero, that is a zero, and upper limit can only be frequency including infinity. On the other hand, broadband transmission or band pass channel, it has a bandwidth with the frequency between f1 and f2. So in this manner, you can differentiate your low pass and band pass channel. So see, you can see the modulation for band pass channel. Since you have a band pass channel, you have a digital signal, but you couldn't transmit this one because it is in the form of digital, and digital required a low pass channel. But since it is a band pass channel, which has a limited frequency range f1 to f2, so you need to convert this digital data into analog data. And over here, it has used ASK modulation, amplitude shift keying modulation. For logic 1, higher amplitude, and for 0, it is a low amplitude. And then it is being transmitted, and at the receiver, inverse it happens. That is, this analog signal, it is converted into digital data by means of this D to A converter. Sorry, A to D converter. Getting, guys? This is a band pass channel, not a low pass channel. If it is a low pass channel, you can directly transmit this digital data. But now you have a band pass channel, so you can't send the digital data directly because it has what? Infinite bandwidth digital data. And analog signal, it has a narrow bandwidth. So that's why you need to convert this digital data into analog signal. Then you can pass it through your band pass channel. Over here, f1 is not closer to 0, and f2 it is not closer to infinity, as I told for low pass channel. So that's why we need to convert into digital to analog at the transmitter side, and at the receiver side, this analog signal reconverted into your digital signal. So remember, digital transmission, it requires low pass channel, and analog transmission requires a band pass channel. Most important thing. So guys, today we have studied about your types of signal, that is analog, digital. Then we have studied the different way we can represent your periodic signal, non-periodic signal, or sinusoidal signal in mathematical form. What is composite signal? How you are going to transmit your digital and analog data using a low pass or band pass channel. So all these things, guys, we have studied in this lecture. So this is the second assignment. So please note down this assignment. And you have to submit this assignment. In next module, guys, we are going to discuss multiplexing and its types. And then we are going to see the analog transmission of your signals. Transmission of signals, there are two ways, analog and digital. So first we would cover the analog transmission of signals. So you can post these assignment to this email address. So thank you very much, guys, for today's lecture.